Hi everyone, welcome to lecture number 5 for Physics 151. This lecture introduces a new kinematic topic, a new kinematic quantity, which is acceleration. We'll also talk about how we graph acceleration and its relationship to graphs of velocity. We'll continue these topics in the next 2 lectures for the specific case of constant acceleration and freefall. In this lecture, I'll show a number of examples from tutorial number 5. So please try the additional sample problems in tutorial 5 and compare them to the posted solutions. Whenever you feel comfortable, go on to the 4-credit problems in online homework number 5. But before we get into acceleration, I have a couple review questions for you to review the relationship between velocity and position and displacement that we talked about in the previous lecture, in the previous couple of lectures. So pause this lecture now, read this question, and do your best to answer. Okay, I hope that the answers that you got were these two. First of all, just as a reminder, for average speed, the definition is distance traveled divided by the amount of time it takes. In this case, there's no formula for distance traveled, remember, in most cases, so you just have to do it by inspection. So we see that the runner jogs 3.5 kilometers followed by another 3.5 kilometers. So the total distance traveled is just the sum of those two individual legs. And then the amount of time it takes is 1 hour in total. So it looks like that the average speed of the runner is 7 kilometers per hour. However, for average velocity, do you remember what the formula is for that? It's displacement over time. So that's the runner's final position minus the runner's initial position, which we can call x initial or x naught. Either one is fine. Notice that this runner ends up finishing exactly where she started. So therefore, the displacement of this runner over the entire trip, the net or total displacement, is just 0. Okay, one more review question. Pause the lecture now and study these 4 graphs of different objects that are all moving simultaneously along the same straight line path, which has the x-axis laid along it. Assume that the objects can either pass each other or pass through each other without actually colliding. And then try and answer the 5 questions on the right. Pause the lecture now. Okay, let's take a look at these questions on the right side. Which of the objects ever reaches the fastest speed during the time shown? Well, when you have a graph of position versus time, like we have here, where can we get speed or velocity information from this graph? Remember that velocity is at all times, the instantaneous velocity is equal to the slope of the position versus time graph. Speed is just the magnitude or absolute value of that velocity. So, put another way, when we're looking for the fastest speed, what we're looking for then is the steepest slope. So, is there one of these that has a steeper slope than all the others at some point, or maybe are there 2 or more that are tied? I think that it looks like object number 1 has the steepest slope right here near the very end of the travel shown on this graph. Okay. Notice that the steepness of object 3 and the steepness of object 1 match around here. Okay. And the steepness of object 3 also doesn't change. The steepness of the slope of object 4 seems to be the same as that of object 3, but just negative in value. And then, of course, what's the slope of object 2? That's just 0. So let me clean up the graph a little bit. So it looks like that the fastest speed reached by any of these objects is that of object 1. Which of the objects is ever at rest, even if just for a moment? Well, again, this is a graph of position versus time. So, and when you see the phrase at rest, what does that tell you about the kinematic quantities of an object? That tells us that the speed or the velocity has to equal 0. Okay. Now, an object can be continuously sitting at rest. So over time, its velocity is continuously 0. Or it can be momentarily at rest, where the velocity is 0 for just an instant. For example, if it's turning around between going backward to forward or forward to backward. Well, are there any points on this graph where the velocity is 0? That would mean that the slope would be equal to 0 for a position versus time graph. So yeah, it looks like for object 2, the slope is 0 the entire time. And for object 1, it looks like the slope starts out at 0 at the very beginning. So I think the best answer here is B. Object 1 is very briefly at rest at the start of the problem, at the start of the scenario shown here. You can think of this as like a movie playing from left to right as time proceeds forward. And then object 2 just sits parked continuously at rest at whatever position this is right here. All right. Clean up my graph just a little bit. Okay. Okay. Part C, what occurs at the moment indicated by the red circle? Well, we can sort of do these by trial and error. Option A, car 1 passes car 2. Well, when we see passes, what does that mean? That means that car 1 and car 2 must have the same position. And this is a graph of position versus time, so that means they should have the same value along the position axis. Is that true? Yeah, that's exactly true. They're both located at the place where car 2 is in fact parked continuously the entire time. So you could think of it another way. Car 1 starts out at this position down here, and then its position changes in the positive x direction at all later times. At the moment shown here in the red circle, that's where car 1 is passing car 2, where car 2 has been parked the whole time. What if we imagine this next option here? Car 1 has the same velocity as car 2. Well, where do we get velocity on this graph? Velocity would have to be the slope. Okay. Are there any pairs of graphs of the 4 graphs? Are there any of the 4 graphs that have the same slope at the same time on this graph? Yeah, it looks like there is, very briefly. Just like we mentioned earlier, car 1 and car 3 look like they have the same slope at around this time right here. Okay. So at that moment, car 3 and car 1 have the same velocity. But that's about it. I don't notice any other ones. Okay. But definitely this is not true. So in that case, option A is correct and option B is not correct. Okay. Part D, true or false? Object 4 reverses direction once during the time shown. Well, when I look at the graph of object 4's travel, what I see is an object that starts at some initial position, right, which happens to be in positive x territory. And then at all later times, it's moving to a more and more negative position. So at a later time, its position is more negative. At a later time, its position is more negative. At a later time, it passes the origin, and then at later times, its position is even more negative than that. So at all later times, the position of object 4 becomes more negative than its initial starting position. But so it doesn't seem to me that object 4 reverses direction at all. Put another way, when you reverse your direction of travel, you have to change from either a forward velocity to a backward velocity or vice versa. You have to go from a backward to forward velocity. Well, where would we get that velocity information off this graph? Once again, it'd be the slope. And we can see that the slope of object 4's travel is at all times, the slope of this graph is at all times the same constant negative value. So therefore, this is an object that is simply moving backward in the negative direction with a constant velocity at all times, never slowing down, speeding up, or definitely not reversing direction. So this seems to be false. Okay. What about part E? Objects 3 and 4 have the same speed, but opposite directions of travel at all times. Okay. Well, speed is the magnitude or absolute value of the velocity. So, and velocity is the slope of these graphs. So if we look at the slope of object 3's graph, we see that it has a constant slope at all times. So therefore, it must have one constant velocity at all times, and it's positive. It's moving in the positive x direction. Whereas for object 4, it has one constant negative slope at all times, so it's moving in the negative x direction. And if I eyeball this on this graph, if I just look at what the steepness of these two slopes are, it looks to me like they are equally steep. So therefore, the speed of object 3 and the speed of object 4 are the same because their two slopes have the same steepness, but one is positive and the object 3 has a positive slope and object 4 has a negative slope, so therefore they are moving in opposite directions of travel. Object 3 is moving in the positive x direction at all times, and object 4 is moving in the negative x direction. So, true. Good. All right, moving on to our topic for today, which is acceleration. So, first of all, acceleration is, well, how do we mean about by acceleration when we say that term? Well, let's think back to our definition of velocity and use that as an analogy to leapfrog us forward to acceleration. So remember that the definition of velocity is the rate at which an object is changing its position, right? Where position is simply where it's located in space. So velocity was expressed as a rate of change with respect to time, okay? How much does the position change, delta x, in a particular amount of time, delta t? Acceleration is a rate of change of the velocity. So you could think of the velocity again, it's possible for something to have a constant velocity if it's coasting along at a constant speed. And in that case, that its acceleration would be zero because its velocity, that object's velocity would never be changing at all. But in a lot of cases in real life, we change our velocity, right? Here, for this race car, the velocity is going from a slower speed to a faster speed over time. So this velocity seems to be increasing over time. So we would say that this car is accelerating. It has a changing velocity as time goes on. You can think of this from a driver's point of view. We use a lot of car examples because a lot of us have experience driving or at least riding in cars, and you could think about what is this driver doing? If the driver were maintaining a constant speed, that would be keeping your foot either off the gas if there were no friction, but most cars have some amount of friction. So we just put our foot on the gas just a tiny bit so that you can overcome that friction and you keep your speed constant. In other words, you keep the speedometer reading the same and your car is moving along at a constant speed. That would be an acceleration of zero. But what happens if you actually press your foot on the gas by a significant amount? If you hold your foot on the gas with the gas pedal down, then your speed is going to climb over time. You'll look at your speedometer and you'll see your speed increasing over time. That's an acceleration. And the rate at which that speed is increasing is our rate of acceleration. And we can express that mathematically. And we'll do an example right down here in just a moment. If, on the other hand, you were to apply your foot to the brake pedal, and you would notice that your velocity over time is decreasing, then that is also an acceleration. That is a negative acceleration, or in common speech, we often call that a deceleration. Okay, so that's also an example of an acceleration. It's anytime your speedometer reading is changing over time. Now you might think we could sort of take this another step, this whole thing. What if instead of keeping your foot on the gas at a constant angle, what if gradually over time you sort of press your foot on the gas farther and farther and farther and farther? In that case, what would happen is the rate of acceleration would then change because you're not keeping your accelerator pedal, your gas pedal at a constant position. You're in fact increasing it. Or what if you let your foot off? Suppose that your foot was, you had the pedal to the floor and you let your foot gradually off the pedal slowly over time. That would also be a rate of change of acceleration. And you can do the same thing with the brake pedal. What if instead of keeping your foot on the brake at a steady sort of level, what if you gradually pressed harder and harder on the brakes or less and less hard? Those are collectively examples of changes of acceleration over time, and those are called jerk. There is actually a name for that. That's jerk. We're not going to do any jerk problems in this class. We're going to assume that all of our, well, we're going to assume that we're going to be doing a lot of examples with constant acceleration. In all of those cases, the jerk is 0. But we're also not going to learn any formulas for that. I just want you to know that there is a name for that, and it certainly is possible to create that situation in everyday life. Okay, so let's think about this rate of change of velocity. Suppose that I were to tell you that there's a car here. It has an initial velocity of 0 when we start our little movie right here, when we start our scenario. And what if I were to tell you that the acceleration is 15 kilometers per hour per second? Okay, so notice that acceleration needs to be a rate of change of velocity. So the numerator has units of velocity and the denominator has units of time. So it's a rate of change over time of velocity. If knowing that little piece of information, can you tell me what this car's velocity should be 1 second later, 2 seconds later, 5 seconds later? Okay, pause the lecture now, think about this, and I'll come back with a hint, and then I'll pause, and then we can pause again, and then we'll talk about the answer. Okay, so first, how would we calculate this? I'd start with the car's initial velocity, and then every second that goes by, I would need to then change the velocity by this amount, 15 kilometers per hour. And notice the plus sign is not written. We usually don't write it, but that's understood. So in other words, I need to increase the velocity by adding 15 kilometers per hour for every second that goes by. So when you think about that mathematically, it would look kind of like this. We start with the initial velocity, whatever that might be, and it says, in this case in the problem, it says that that's equal to 0. And then we would add 15 kilometers per hour for every second that passes. So after 1 second, how fast would this be? After 2 seconds, how fast would this be? Okay, pause again if you don't have the answers yet, and calculate what it would be for 1, 2, and 5 seconds. Okay, I hope that you got 15, 30, and then if you do this 5 times, 75 kilometers per hour. Notice again, our initial velocity that we're starting with here is 0, so we're plugging in 0 for all these initial velocities. I'm sorry, this graphic is from a different book, so they used a 1 here instead of a 0, but these should be 0. Now, I just wanted to point out briefly, what if we wanted to find the time at 1.5 seconds, or I'm sorry, the velocity at 1.5 seconds? As long as the acceleration is constant, right? In other words, as long as this driver's foot is on the gas pedal at a constant level, right? You hold your foot at a constant angle, then that means the acceleration of the car will probably be one steady constant value at all times. And in that case, we can slice this by fractions of a second, right? For every half second that goes by, the car's acceleration will increase by 7.5 kilometers per hour. So I could, at t equal 1.5 seconds, it would be 15 plus 7.5, right? Or 22.5 kilometers per hour. We could do it by tenths of a second. For every tenth of a second, the velocity would increase by 1.5 kilometers per hour per tenth of a second, and so on. So yes, for constant acceleration, we could interpolate like that and figure out what it would be for any fractional time also. Let's do one more quick example. What would be the, given again, the acceleration of this car right here, notice that this car's initial velocity is not 0. Now it's starting with some initial forward velocity. Given an acceleration of negative 2 meters per second, what would be this car's velocity after 1 second, 2 seconds, or 5 seconds? Okay, once again, pause the lecture and see if you can do it without a hint. Okay, so this is what 2 meters per second means. Now notice in this graphic, they've already gone ahead and written the acceleration in a more compact mathematical form, and we'll talk about that coming up in a few slides. But what this represents, the second squared in the denominator, there is no real meaning to time squared. What that is just a mathematical compact notation for meters per second, meters over seconds in the numerator, then divided by another second in the denominator. So this is meters per second per second. So that would be -2 meters per second every second that passes. Okay, after 1 second, then this would be what? Go ahead and pause and calculate if you haven't done it yet. Okay, so after 1 second, this would be 15 minus 2, or 13 meters per second. After 2 seconds, this would be 15 minus 2, which is 11 meters per second. After 3 seconds, we subtract another 2 meters per second, and that's 9, and so on. And then 7, and then 5. So you can see after 5 seconds, the velocity is going to be 5 meters per second. So what is the driver doing in this case? Is the driver using the gas pedal or the brake pedal? Right. This driver is braking. This driver is slowing down. Right. At the start of our little scenario, the driver was going much faster, and now at the end, the driver is going much slower. By the way, in case you're wondering what these speeds are like, 1 meter per second is a little over 2 miles an hour. So this driver has just decreased from 30 some miles per hour down to about 10 some miles per hour. Now, again, I want to mention that a lot of people would call this a deceleration, because in everyday parlance, we would refer to the decreasing of the speed of an object as a deceleration. So when things slow down, they decelerate. And you probably heard that in driver training class and things like that. When you press the brakes, you're decelerating the vehicle. All right, but we're going to find out later that from a mathematical standpoint in physics, deceleration does not always mean the same thing as a negative acceleration. Right? In fact, specifically, that's only true if the car is facing forward, or I'm sorry, yeah, if the car's velocity is in the forward direction, not if the car's facing forward, but if the car's velocity is in the positive x direction to begin with, then slowing down would be negative acceleration. But if the car has a negative velocity to begin with, then this is not true. Slowing down would be a positive acceleration, and we'll see some examples coming up. So to avoid this potential confusion, right, some people mistakenly think that deceleration means a negative sign on the acceleration. That is not true. For all of our free fall problems, our objects will sometimes be speeding up when they're falling downward, but they always have negative acceleration if we choose our axis to be upward. So to prevent that confusion, I'm just going to avoid the term deceleration in this class. I will not use it usually when I'm speaking, and I will definitely not use it in any written materials. Okay, this is just one quick little reflection on the fact that this is a repeat from earlier about the definition of acceleration. And this is a reflection on the fact that acceleration can apply to other quantities as well. So, for example, we often hear about the rate at which an amount of money changes as being an interest rate if you're earning interest, or if if you're gradually being assessed a fee at a certain rate, right? Or your wage rate would be how fast, what is the rate at which the balance in your bank account increases if you receive a certain amount of wage. So if you imagine getting paid instantly instead of at the end of the month, or twice a month, then what would the balance in your bank account do, right? If you're earning $13 an hour as an undergrad, for example, then your rate of increase of your balance is going to be positive $13 per hour. What if your wage rate or interest rate or payment rate or whatever it might be, right? If it's a accumulation or a deduction, what if that were to change over time? So what if you had some interesting incentive structure where this week you're being paid $13 an hour, but next week if you maintain satisfactory performance, next week you earn $13.10 an hour, and then the following week you earn $13.20 an hour. In that case, you have a rate of change of a rate, and that would be an acceleration. And specifically, what would this acceleration be? It looks like you're gaining 10 cents an hour every week. So that would be your acceleration. 10 cents an hour a week. You can hear this all the time on financial channels or on the news when they talk about the rate of change of inflation, right? Inflation is kind of like a rate at which money becomes less valuable, or the prices of things, common things go up. But then people will talk about disinflation, right? And disinflation is when the rate of inflation goes down over time. So that would be a negative acceleration. Okay. Here's the problem number one from our tutorial. So these are sample problems. And let's work through this one together really quickly. If you ever are looking at slides instead of watching videos, then of course you won't see my handwriting and everything up here. So just look at the posted solutions for tutorial 5. Okay, suppose that your car starts with an initial velocity on an on-ramp of 5 meters per second, and that's what we're going to define as the initial velocity v naught at time t equals 0. So that's when our scenario begins. Okay, so you don't start from rest in this case. You already start with some forward motion. And then suppose that you hold your foot down on the car's gas pedal at such a position so that your car accelerates at a constant rate of 3 meters per second per second. What is your car's velocity at the end of each successive second? Well, we already know what this means now. We know that this means that for every second that goes by, we need to increase our velocity by 3 meters per second for every second that passes. So this is a sort of addition we don't need a calculator for. We can just do this in our head. After 1 second has passed, we need to add an additional 3 meters per second, and that will equal 8 meters per second. And after another second goes by, we'll add another 3 meters per second, and this will equal 11. And so on. Do you think we could write or figure out a way to write an algebraic function that would sort of describe what this car's velocity is over time? So could we say, okay, at any future time t, the velocity of the car is going to be equal to what? Well, what was the sort of mathematical algorithm we just used here to calculate all of these later velocities? We started with the initial velocity, so we could say, okay, let's say that we're going to start with 5 meters per second. And then what did we do? We added to that initial velocity 3 meters per second multiplied by the number of seconds that had elapsed, right? That was how many times we added 3 meters per second. So we could say, okay, at some later time t after our starting point, after our initial moment, right? If we know what that time t is, then we just have to multiply 3 meters per second by that many seconds of time. And this would work, right? We've just sort of cooked up just by using, just by sort of thinking this through, we've cooked up an algebraic function that would give us the velocity v at any later time t. Okay. Oh, I'm sorry. This is meters per second squared. Okay, per second. Okay, so this could be written a little more formally if we were to say, okay, our 3 meters per second here, let's call that acceleration. We'll call this value a. So that's going to become that value there. And let's call our velocity at the start of our sort of scenario at time t equals 0, v0. And what we'll wind up with is this is going to be equal to v0 plus a times t. It turns out this is going to be one of the formulas that we're going to learn in lecture 6 for constant acceleration. As long as the acceleration remains constant, you can use this formula over any fraction of a second t as well. Okay. Let's mathematically define acceleration a little better. Okay. Up until now, we've been just using a sort of common sense definition of it based on its units and what we want it to mean. So I'm just reminding you, this first part up here is a reminder of what we have from a previous lecture, and that is, position is our x or y or z Cartesian coordinate, and just a quick little reminder that it can be to the right of the origin or to the left of the origin, right? It can be positive or it can be negative. Then um, velocity is defined as the change in position over the change in time. And that change in position part we call displacement. That has its own name. Okay. Instantaneous velocity is the amount of change of position over time over an infinitesimally small amount of time. So your speed at any moment in time is the absolute value of your instantaneous velocity. And that's how fast you're moving at that instant. Maybe we can use this definition here by analogy and say if velocity was the rate of change of position with respect to time, if we want acceleration to be a rate of change of velocity, maybe we can do something similar. We'll say, all right, we'll just put the thing we want, the thing that's changing in the numerator, and then in the denominator we have time, and maybe that'll work. Okay? And sure enough, yes, that's exactly what we do. We can say that the average acceleration of an object over some period of time is equal to its final minus its initial velocity. So remember, delta is always a final minus initial. Okay, or v minus v0 is also something we're going to use a lot. And then if we were to shrink the time down really to a really infinitesimal interval, then you get the instantaneous acceleration of an object, and that's how fast it's moving. That's how fast its velocity is changing at a particular instant. Now again, many of the examples we're going to be doing are going to involve a constant acceleration over time, so the acceleration itself won't vary, but it's very easy for the acceleration to vary in real life, and there will be some examples like a mass on a spring, for example, where the acceleration will vary a lot. So we just, in order to deal with those cases in general, you need calculus. So when the acceleration varies over time, then you need derivatives and integrals to deal with that. Just like when, for any general case, right, you would need this earlier definition of velocity as being the derivative of position with respect to time. Okay. But we're good. Again, this class does not use calculus, so I just know that many of you have already had calculus, and I know that these definitions are actually taught in most calculus textbooks as well during Calc 1. So many of you, probably half of you, have already seen these definitions on the right. Okay, now before we leave this slide, let's think for a second about the units. What should the MKS units of acceleration be? If either think back to what we just saw on the previous slides and see if you can remember, or think about it from dimensional analysis. Look at our formula and ask yourself, what are the MKS units of velocity? What are the MKS units of time? And then divide. Okay? All right, I hope that you agreed that it's meters per second squared. Now, this is what you would have had before you simplify it. We have meters per second in the numerator, and then in the denominator we have some other, we also have time. Again, if we just stick with MKS units, that will also be seconds. But you saw on previous slides we had an example of kilometers per hour divided by seconds. And in that case, the hours and seconds don't mix unless we convert, right? We'd have to convert the hours into seconds, and then we can combine them. Okay. So you can have other examples. You can have miles per hour divided by seconds. That would be a car. When we say that a car goes from 0 to 60 in 4.5 seconds, that would be an acceleration of 60 miles per hour divided by 4.5 seconds. And you could divide that and find out what it is in miles per hour per second. So those are all examples of accelerations. What I want you to do is always think about acceleration as being a speed per a change in speed per time. Okay, so how much faster or slower is an object getting per amount of time that goes by? But when those are all MKS units or CGS units, we're always going to mathematically combine the two like time units in the denominator and write it in the more compact form of distance over a second squared. But I want to emphasize the fact that time squared doesn't really have much meaning, right? There is no like intuitive physical meaning for time squared. So that is just a mathematical compactification. And because algebraically, these two expressions are exactly the same algebraically, okay? But mentally, we always think about it like this on the left side. Now, we've mentioned that velocity can be positive or negative. Do you remember what the meaning of that was? When an object's velocity is positive versus when its velocity is negative? I hope that you recall that when an object is moving in the positive x direction, then its velocity is positive, right? If you think of a car facing in the positive x direction, so the headlights face in the positive x direction, that would be a car that's in drive, right? It'd be a car with a forward velocity. If an object is moving in the negative x direction, if it's moving toward the positive, I'm sorry, if it's moving in the direction of negative x, right, along the negative x-axis, then that would be a negative velocity. So in the case of a car that's facing in the positive x direction, that would be a car in reverse. Okay. What does it mean if an acceleration is positive versus negative? Well, mathematically, we can see from this formula that it should mean that a car's velocity should become more positive over time or more negative over time. So what do each of those things actually mean for the motion of the object? Well, it depends on whether the velocity was positive or negative to begin with. Because if the velocity is positive to begin with, well, if the velocity is positive to begin with, for example, then when you make the velocity more positive over time, that object is speeding up. On the other hand, if the object's velocity was positive to begin with and you make it more negative over time, then that object is slowing down. Okay, so these are the equivalent of a car that's in drive and then the driver presses on the gas versus presses on the brake. What if the car's velocity were negative to begin with? Okay, then in those two cases, when you have well, let me ask you to think about that for a sec. Think about this for a second. On the left side, we have a cartoon of a car that is initially traveling. All right, notice that they turned the car around so that the car is facing in the negative x direction right now. But in the analogy I've been using, the car always faces the positive x direction, and this car is in reverse, okay? So what we have is a car that starts out at an earlier time in reverse at a lower speed, and then later the car is in reverse at a greater speed. Okay? What is the sign of the acceleration in that case? Is the velocity becoming more positive or more negative over time? Because that's what the sign of acceleration should tell you. Is the car becoming more positive or more negative? Okay, in this particular case, the velocity is becoming more negative over time. We have a velocity that starts out with a small negative value, and then later, at later times, it becomes a bigger negative value. So that means that the velocity is becoming more negative over time, so therefore the acceleration is negative. In the right-hand case over here, we have a car whose velocity was initially a very big negative value at some early time, and then at some later time, it's a much smaller negative value. So this is a car that's moving in reverse, but it starts out going fast in reverse, and then the driver slows it down. So the driver hits the brakes. So at later times, it's going more slowly in reverse. So in that case, the acceleration is becoming what? More positive over time. So the acceleration is positive. All right, so what we have here is an interesting sort of combination of situations where the positive accelerations, for a car that's moving in the positive direction, a positive acceleration means speeding up. But for a car that's moving in the negative direction, for example, in reverse, a positive acceleration means slowing down, because making the velocity more positive over time means the size of the velocity, that quantity in meters per second, gets less, gets smaller. Conversely, if you have an object that was initially moving forward and we give it a negative acceleration, which is this example in the upper right, then what does that mean? It means that it slows down. So that's, again, a driver hitting the brakes. Whereas if the car is moving in the reverse direction and it undergoes a negative acceleration, then you're making a negative velocity more negative, and that means that the car is speeding up. So that'd be a car that's in reverse and the driver hits the gas. This is just a repeat of what I said a few slides ago, which is that deceleration in common speech usually means that an object is slowing down. So looking at these four situations, do you see which of the situations people might say that the car is decelerating? It looks to me like it'd be the two situations where the car is slowing down, which are the ones on the right. So in that case, yeah, in everyday speech, those are the times when the driver is hitting the brakes. So either the car is going forward and you hit the brakes, or the car is going backward and you hit the brakes. But notice the signs of the acceleration mathematically in those two cases. In one case, the sign is, when the car is going forward, the sign of the acceleration is negative, and when the car is going backward, the sign of the acceleration is positive. So to help eliminate confusion, right? I don't want you to associate deceleration with negative acceleration. That is not going to be true algebraically in our case, okay? So this is not true for deceleration. So what I'm going to do is I'm just going to avoid using, again, the term of deceleration to try and eliminate ambiguity. All right. I think it's time for another example. So let me give you a moment to try and apply our formula for average acceleration from the previous slide. If you can do it from memory, great. Hit pause now and try and calculate what this car's average acceleration is over this time interval. Let's assume that it's 4 seconds long. And there's initial on the right and final on the left. Okay. All right, here's a little hint. I hope that you remember this is a formula from the previous slide. Now, if you need to, pause again and then calculate what the acceleration is. Okay, and I hope that you got the acceleration is, in this case, positive 2.5 meters per second squared. So again, this is one of these situations, as on the previous slide, where we have a car that is moving backward the entire time, but the acceleration is positive, okay? That just falls out from the algebra. Okay. Finally, the last bit of theory for us to cover this lecture is what this means, what the definition of acceleration means graphically when we look at graphs of acceleration or graphs of velocity. So when we look at this slide should look pretty similar to a previous one we had, where we talked about how from the formula for average velocity, that tells us that average velocity is the slope of the position versus time graph. We're going to do exactly by analogy. We're going to do the same thing now. We're going to use our formula for average acceleration, and we're going to say, hey, this part on the right side here looks just like the slope of a line. It looks like a rise over a run if the rise were velocity, right, the numerator here, and the run is time. So if we were to make a graph of velocity versus time, then it would stand to reason that on average over a large time interval, the average acceleration should be the average slope that you calculate over that large time interval. And if we were to shrink that time interval down to be instantaneously small, then you get the instantaneous acceleration at a particular moment in time, t. So again, the instantaneous acceleration at any point on a velocity versus time graph is the tangent slope at the time t. This is just a reminder again of the definition from calculus. Great. So we can summarize this. Oh, almost forgot. I was going to say we're going to most commonly deal with constant acceleration over time. Very rarely will we have a situation where the acceleration is changing in a way where we have an equation for it. In other cases where the acceleration is changing in some unspecified way, we'll then usually deal with average acceleration. But once again, constant acceleration will probably be the most common situation that we're going to encounter. So what I was going to say is we can now take what we've learned here about acceleration being the slope of the velocity graph and add that to what we had before. So from our previous lecture, we had this earlier part up here where we knew that velocity is equal to the slope of the position graph. And because from calculus, we know that the opposite of differentiation is integration. And integration is finding the area between a graph and the axis, and the horizontal axis. So then we can apply that and say that the displacement, which is, it turns out, is the difference between two positions. The displacement is just equal to the area of the velocity graph. Okay, so slope and area in calculus are sort of inverses of each other, right? Slope is differentiation, area of the curve is integration. All right. So now we can add to this analogous definitions. So now notice that items 3 and 4 on this slide look exactly like items 1 and 2, only we've replaced the words velocity and displacement by acceleration and velocity, because we have these analogous definitions now. I want to add that, again, this displacement, when we use this net area method here, all we can get is a delta from that method. What integration doesn't give us is there's always some unknown constant that is not determined. So that would have to be given separately. So this initial position or initial velocity, right, of the delta, because remember, delta is always x at some later time minus x at some earlier time. And this is going to be velocity at some later time minus velocity at some earlier time. What you have to be given is given that initial position or initial velocity. All right, so let's put this to use. We're going to use both the graphing stuff that we just discussed, and we're going to use the earlier definition of acceleration that we had a couple slides further back. So suppose that you're given a graph of the velocity of a race car as a function of time. So I'm sorry if I got cut off here on the graph, but this is time on the horizontal axis. Oh, there it is down the bottom. Okay. So notice that over 60 seconds, this graph covers 60 seconds. You're given what the velocity of this race car is at all moments in time. So first, I ask you, what is the car's acceleration calculated during each of the three time segments? And you can see the three time segments are labeled A, B, and C, right? Just to help us as a shorthand. So use our definition of velocity. Use our definition of average acceleration. average acceleration over time interval a is equal to the change in velocity over time interval a divided by the time of time interval a. So time interval a is 0 to 20 seconds. So that's going to be the velocity at 20 seconds minus the velocity at 0 divided by the amount of time that elapses. So looking at the graph, I can read off what is the velocity at time t equals 20 seconds, right? And what was the velocity at time t equals 0? Well, that looks like 50 meters per second minus 0 meters per second divided by 20 seconds. So that's positive 2.5 meters per second, okay? In the numerator, I have meters per second, and then in the denominator, I have seconds. So when I divide, I get meters per second squared. Okay, now for segment B, we could do the algebra, and it would look something like this, although I'm probably not going to finish it. The velocity at 50 seconds minus the velocity at 20 seconds divided by the amount of time that elapses. Well, all right, let's go ahead and finish it. It'll only take a moment. The velocity at 50 seconds, reading it off the graph, is 50 meters per second, but the velocity back at 20 seconds was exactly the same. And then in the denominator, we have 50 seconds minus 20 seconds. So that's equal to 0 over 30 seconds. So 0. Or just plain 0. Units are optional for me if, oops, I'm sorry, I accidentally cleared that. Units are optional for me if the value is 0. Was there a faster way to do that? I think so. Remember what we just learned? That for any period of, I'm sorry, when you have a graph of velocity versus time, then acceleration at any moment in time is equal to the slope of the velocity versus time graph. So what's the slope of this graph during time interval B? Looks like the slope is just equal to 0. So that tells me that the answer again is 0. In fact, when we calculated the acceleration during segment A, what we were doing is we were also calculating the slope during segment A by taking the rise divided by the run, right? 50 minus 0 divided by 20 minus 0. So we were calculating the slope there as well. I'll leave it to you to calculate what the slope is during segment C. Okay? Although when you check the answer, I mean, first of all my answer choices are negative because we can see at a glance that the slope there is negative. That makes sense. And I hope that you'll get B as the answer, -3 meters per second per second. Now, if I wanted to graph the acceleration here as a function of time at all times, then what I should do is I should create a graph that reflects at all times the slope of the velocity graph above. So from 0 to 20 seconds, I need to graph 2.5 meters per second squared. So that would be here. Okay. And then from 20 to 50 seconds, I should graph 0. And then from 50 to 60 seconds, I should graph -3. And again, I'm not concerned with how you may or may not choose to connect these vertically. And like I said in a previous lecture, it's not physically possible for a car's acceleration to instantaneously change from positive 2.5 to 0 or from 0 to -3. In real life, there would have to be some sort of there would have to be a curved transition here and a curved transition there. In other words, this graph would have sort of a knee like this. And what that would mean for the velocity graph up above is the velocity graph would be rounded off. And you wouldn't have, it's not allowed in real life to have these discontinuities in the slope. Okay, but that's fine. We're just taking a hypersimplified case. Now, try and sort of keep this finished graph in mind, okay? And, oops, I shouldn't have cleared it, but okay, it's fine. So keep that graph in mind. Actually, the velocity graph is still there, so that's great. That's what we want. And let's consider what the motion of the car is like, right? What can we infer about the motion of the car in sort of qualitative language, right? Just talking about it. Um, is the car at rest? Is the car moving forward? Is the car speeding up? Is it slowing down? That sort of thing, okay? Most of that information we're going to get from the velocity graph here, right? As opposed to the acceleration graph. So let's think about this for a sec. Well, actually, a lot of this sort of draws on what was in the previous lecture. So what I'd like you to do is pause this lecture now and try and answer D through H first on your own without me. And then we'll take a quick look at the answers together. Okay, so remember when you want to know when a car is in motion, what does that sort of mean as for a velocity graph or for the value of the velocity algebraically? Well, if a car is in motion, that just means that the velocity is not zero. So basically this is asking over which of these time intervals is the velocity not zero? And it turns out this is a graph of velocity. So it looks like it's never zero during C, it's never zero during B, and it's never zero during all of A except for the very, very beginning. So the closest answer here is E, with the exception of the moment when T is equal to zero, okay? Conversely, algebraically, how do we know when an object is sitting at rest? Well, that is when the velocity is identically equal to zero. And that can happen over a continuous period of time if we're talking about sitting, or it can happen instantaneously, very briefly, if an object is, say, turning around, if it's changing from positive to negative motion. Okay. So are there any time intervals here when the object is sitting continuously at rest, where the velocity is just hanging out at zero? Right? Well, it looks like the answer to that is no. Right? The car is in motion. It's going positive. It's in the positive direction. Oops. It's moving in the positive direction during C. It's moving in the positive direction during B. Right? These are all positive velocities. And it's moving in the positive direction for all of A except for the very, very moment, the instant at the start when the car started from rest. But that's it. So the one exception, the answer is none of the time intervals, but the one exception is at the moment T equals zero. All right, during which of the time intervals is the car moving forward? What would that mean algebraically for the velocity? Well, that would be moving forward, moving in the positive direction means that the car's position is becoming more positive over time. So that would mean the velocity needs to be greater than zero. Okay, because remember, velocity is the rate of change of position. So during which time intervals does that occur? It looks like the velocity is greater than zero during all three of the time intervals. Okay, again, ignoring that the instant at the very start when the car was momentarily at rest. What about a constant speed? Okay, constant speed would mean that you have, right, speed for instantaneously, at least, speed is equal to the absolute value of the velocity. And again, we're not going to use s for much longer. Soon we're going to replace s with just plain v for speed. But it's the absolute value of the velocity. So if the speed is constant, that means that we need to have a constant value for v over time, right? If you're coasting at a constant speed, then the implication there is that there is an extended period of time over which the speed is constant, or velocity is constant, right? So it looks to me like the velocity maintains one constant value of 50 meters per second over time interval b. So that would be time interval b. What would you say is happening to the velocity during time intervals a and c? During time interval a, the velocity is becoming more positive over time, and during time interval c, the velocity is becoming more negative over time. Now, do either of those correspond to speeding up, right? Or I could have asked slowing down. Well, again, the speed at any moment in time is going to be equal to the absolute value of the velocity. So speed, if the velocity is positive, that means that speeding up would imply increasing velocity. So let me write it that way, right? So if the velocity is positive, then speeding up implies increasing v, right? If the velocity is negative, then speeding up implies more negative v. So actually, a better way to put this is more positive over time. All right. Put another way, speeding up means getting farther from the origin here, which is rest. Okay, rest is velocity equal to 0. So to speed up over time, you need to get farther from rest, which is right here, at velocity 0. And farther from rest could be in the reverse direction, or it could be in the forward direction. So this would be speeding up, that would be speeding up, all of these would be speeding up over time. Slowing down, so that of course is A only. Slowing down would be getting closer to a velocity of 0 over time. So slowing down would involve this time interval here, where as time goes on, we're getting closer and closer to a velocity of 0. So there's a lot of ways to look at this, right? You could look at it algebraically, as far as the value that the velocity has. You could think about things qualitatively, right? Are you getting closer to a velocity of 0 or farther from velocity of 0? You could think about it more algebraically, right? If in order for s to increase, then v has to become either a bigger positive number or a bigger negative number. That would allow s, the absolute value of v, to increase, and so on. Let's consider let's go back now to problem 2. So I took these out of order. I did problem 3 first. Doing problem 2, suppose that we start with a small toy rocket, and it starts with an initial velocity of positive 50 centimeters per second. So that means that as we start our scenario, start our movie, this little toy rocket is already moving forward, right? At the moment we start our sort of story here. Also, remember, this is all one-dimensional. So the x-axis is laid out along a guide wire that the rocket can move forward or backward on. So this rocket isn't moving up and down vertically, it's moving horizontally, okay, along some sort of a guide wire. All right, notice that the little rocket experiences a strong headwind which blows against it with a constant, and causes it to undergo a constant acceleration of negative 15 centimeters per second per second. So if we think about what's happening here, this rocket starts out from wherever its initial position is, okay, and we could think of it as having a little maybe a little thruster on the back or something, or actually the thruster is not firing, so it has little fins. I'll just draw some little fins on the side. This is the nose cone over here, okay? And it's on some guide wire, right? And it starts out with an initial velocity of positive 50 centimeters per second. And then as time goes on, it's going to slow down because there's an acceleration of negative 15 centimeters per second at all times. Okay, so after 1 second, the rocket's going to be going a little more slowly. It'll have moved over to the right. And then after another second, it will move further to the right, but it'll be going slower still, and so on and so on. And then this question asks, at what time does the toy rocket's velocity finally reach 0? By the way, what will happen after that time? If the wind keeps blowing, then this acceleration will keep on making the velocity of the rocket another negative 15 centimeters per second every further second that goes by. So that means the velocity will turn around and become more negative, and I'm sorry, it's always become more negative. The rocket will start to actually speed up, but it'll speed up in the negative direction. Okay, so let's solve this now using the formula that we already know. So we know that average acceleration is equal to change in velocity over change in time. Okay, and spelling this out, I'm going to say that the right-hand side of this is equal to v final minus v initial divided by the amount of time that passes. Now, if we stipulate that the acceleration is constant, then we can get rid of this little average down here. And we can just say the average of a constant number is just the constant number. So you'll see this, us do this all the time, where we drop the average off of a value that we've already know is a constant value. Now, which of these items do we know and which are we trying to find? Okay, well, we already know V naught, we already know the acceleration. So acceleration is known, V naught is known. We want to know at what time is the rocket's final velocity? Well, it's not final as an end of the whole trip, but at what time is the rocket's velocity equal to 0? So V final is known, that's going to be 0, and then we can solve for t. Okay, so let's now do a little more algebra and say that V final, I'm sorry, we want to find t. T is equal to V final minus V initial divided by A. Okay, so I've isolated my value for t, and I found an expression for that. And everything on the right-hand side is known, and the only unknown I have is the thing I want to solve for on the left-hand side. So let's go ahead and plug in our values now. V final is 0. V initial is positive 50 centimeters per second. And the acceleration is negative 15 centimeters per second squared. Now notice I can watch my units cancel because I'm putting units on all my quantities here. So centimeters cancels, one of the seconds cancels, and I'm left with seconds in the denominator of the denominator. So that's going to be the numerator. Also, the minus sign cancels, and I have positive, and I have positive, which I want for time, right? Because a negative time really wouldn't be physical, right? Our whole scenario starts at 0 seconds. And the value I get is positive 3.33 and so on seconds. Now, we can ask ourselves, okay, what about significant figures? It looks like the value in the numerator had 2 sig figs, in the denominator had 2 sig figs. So I'm going to round this to 2 significant figures. 3.33 seconds. Oops, I'm sorry, I said 2 significant figures. I apologize. Great. All right, so now we know what's happening. This rocket, over the first 3.3 seconds, this rocket slows down. Oh, sorry. Didn't mean to erase that. During the first 3.3 seconds, this rocket slows down, slower and slower and slower and slower, and then at 3.3 seconds, it pauses. If the headwind keeps on blowing after that, then the rocket will start to speed up in the negative direction, and it will get faster and faster and faster as long as that headwind keeps on blowing. Okay, So it slows down slower and slower and slower, and then it turns around, and then it starts to increase in the negative direction like that. That leads us to the next question, which asks, if the acceleration maintains, right, if the headwind keeps on blowing, what will be the rocket's velocity at 6 seconds? So based on our little qualitative description that I just gave you, we know that it's going to be some negative value, right? So we would expect the velocity to be negative. So same thing. Let's try and set this up starting with our definition of average acceleration. Average acceleration is equal to delta v over delta t. Okay. Once again, we're going to drop the average. So acceleration, because it's constant, acceleration is equal to v final. Now in this case, our final time is at 6 seconds. So a lot of times we'll start writing that as v at time t, or just plain v, minus v initial divided by the amount of time. So what should I recommend, think to yourself, which of these quantities do we already know, and what are their values, and which of these am I trying to solve for? So I recommend that you pause, isolate the variable that you're trying to solve for, plug in the values, and complete this. If you get stuck, or if once you get your final answer, then continue the lecture. Okay, so let's figure out what we know and what we're trying to solve for. We're given that the time t is 6 seconds, so we know that. The acceleration is the same as it was before. We still know that. V naught, the initial velocity, is still known. And we're asked actually to find the velocity at time t equals 6 seconds. So that's the unknown that we're trying to solve for. So let's isolate that. V final is equal to, it looks like, I will multiply both sides by delta t, acceleration times delta t, plus, and then I add v naught to both sides, v naught. Okay, so now I can plug in my values. So that's acceleration. Delta t is 6 seconds. V naught is, and again, you don't need to write these plus signs on the starts of our values. I will sometimes do it in some cases just for emphasis. Okay, like I put it up here in the initial description of the problem. Okay, so it looks like that's negative 90 centimeters per second. I watch my units cancel. Okay, plus 50 centimeters per second. And that should be negative 40 centimeters per second. Looks like my sig figs just carried along, so it's 2 sig figs. Good. Good. So sanity checking, yes, we already said at the very start that we would expect this to be negative. So that's exactly what we got. All right. Finally, if we, I say, given the same situation with the rocket, let's try and construct a position, a velocity, and acceleration graph for the rocket over 10 seconds. Okay? So, well, actually, I guess I don't specify the amount of time here. I should have specified that in the actual problem, in the question. What I'm going to do is I'm going to graph it over 10 seconds because that will encompass everything that we've talked about in parts A and B plus more. Okay? So, first of all, I give you a hint. The acceleration graph should be done first because it's going to be the easiest. And then the velocity will be the next easiest and next simplest, and the position will be the most complicated. So I recommend doing them in that order. So first, what should the acceleration graph look like in this case? All right? Well, we're told that the acceleration has a constant value of negative 15 centimeters per second squared at all times. Well, then I want to draw a graph that does exactly that. So I want to create a graph that is a straight line at negative 15. I'm just going to draw it over here. Negative 15 centimeters per second squared at all times. That's it. My acceleration graph is now done. Okay. Now, let's assume that this time axis here is about 10 seconds long. Okay. So in that case, this is about 10 seconds here.
in which case this is also about 10 seconds. These should all be to the same scale on the horizontal time axis. Okay. The vertical scales are totally different because they're totally different quantities. We have acceleration on the right, velocity in the middle, position on the left. But horizontally, the horizontal axes should all be the same. Now, let's construct the velocity graph. First of all, we can plot points for the values that we already know. So we're told in the description of the problem that, I'll change to green here. We're told in the description of the problem that the initial velocity is positive 50. Okay, good. So that means we need to have some sort of initial point up here at positive 50. Then we also solved in the previous, in part A, we solved that the velocity is going to be 0 at t equals 3.3 seconds. So that's a third of the way along this time axis here. That's when the velocity is going to be 0. And this is at t is 3.3 seconds. And that's our velocity 0. Also, just for good measure, at 6 seconds, we also know that the velocity was at negative 40. And that's what we solved for in part B. So if we wanted, we could also plot that as well. Okay. So what else do we know about the velocity graph? I mean, at this point, we could make a little leap and say, well, you know what? We know the acceleration is constant, so that means a sort of continuous, steady rate of change of velocity. And it looks like these 3 points here sort of define a line. So why don't I just draw that line, right? At least as far as I want the graph to go. Or we could also say acceleration should always be the slope of the velocity graph. I see that my acceleration graph here has a constant value of negative 15 at all times. So that means I need to have a velocity graph that is a graph whose slope is a constant value of negative 15 at all times. How do I do that? A straight line with a negative slope. So sure enough, another way to think about this is that the slope of this graph must be negative 15 always. All right. So how do we get that? Straight line. So in that case, you just need to have one anchor point, right? Either here or there or here, and then you can draw a straight line of a slope of negative 15 through it, and you're done. Okay. Now, we can use the same sort of approach to qualitatively construct our position plot here. Okay. Now, for the position plot, I give you a little more information. I also say, let's switch to, say we'll switch to, I guess we'll switch to black ink for this one. Okay, so I say let's go ahead and start, let's call the rocket starting position the origin, because we haven't needed that until this point, right? So I never mentioned until now what the rocket's position is at any moment in time. So let's say it starts at the origin. Then that's the only position we know at this point, right? We haven't calculated its position at any other time, and nor have we sort of learned formulas to do that yet, although we will in the next lecture. But qualitatively, we can figure out a bunch more stuff just knowing the relationship between the velocity graph and the position graph. So can you fill in the blank for me? Velocity, at all moments in time, velocity is equal to the blank of the position versus time graph. Okay, well, I hope you said slope. So what does that mean for us? That means that at the initial time at t equals 0, the velocity has a value of positive 50. So that means I need to draw a graph whose slope starts out at positive 50, right? So a nice steep positive slope. Then at t equal 3.3 seconds, I need to make this graph have a slope of 0 because the velocity is 0. So that means the slope needs to be 0. Then at 6 seconds, I need to make sure that the slope is negative 40. So that would mean something like this, like a pretty steep negative slope. And if I look at the entire graph over here of velocity, I can actually think about all the times in between. I can say, all right, I need to have a graph whose slope goes from positive 50 to a smaller positive number to a smaller positive number to a smaller positive number, hitting 0 at 3.3 seconds. Then it's a bigger and bigger negative value, bigger and bigger negative value at all later times. Okay. So what we wind up with, let's see if I can just choose a really big marker here. What we wind up with is a graph that looks sort of like this. Where at all moments in time, the slope of that graph is going to be equal to the velocity value. Okay, so starting off with a slope of positive 50, and then a slope decreasing to a slope of 0, and then increasing to a slope of negative 40, and then increasing to a more negative slope beyond that. Quick little side note, if you've had some calculus, then you can ask yourself, okay, what's the mathematical function that is, that has a derivative that is a straight line? And the answer is a quadratic or parabola. So that's exactly what this is right here. This is a quadratic or a parabola, and this is the apex of the parabola. Right? And if we take the derivative of this to find the velocity at all times, we would get a linear function. And if you take the derivative of the line, you would get a constant. So if you also know calculus as well, you can use some calculus to double check these. Okay, by the way, to foreshadow, this set of plots is exactly going to be exactly like one of the sets of graphs for problem 4. So for problem 4, there's one of the graphs that asks, okay, suppose you have an initial starting velocity. Oops, let me change color here. Suppose you have an initial starting velocity, and then at all times you have a negative acceleration. What should the graph of acceleration, velocity, and position look like? And you'll end up getting a set just like this. But I encourage you to work through the thought process again, using the principles of what we know about the slope and the area rule. So that brings us to question 4. So for problem 4, I'm only going to do a couple of the examples. I'll leave the rest to you to try on your own. So again, suppose that we have an object that travels along a straight line path. Suppose that we give a little bit of information. We say that initially, suppose it's a straight line road, this little car. Suppose it starts off with a constant negative velocity, and it maintains that constant negative velocity at all times. So we're calling it v naught, but v naught has a negative value. Okay, so it's a variable with a negative value. Also assume that the car starts at the origin, which I did for all these problems. I started the object at the origin just to make things simple. So graph the rest of the position and the acceleration graph for this little car. Okay, well, first of all, let's do acceleration first. That should be pretty straightforward. Acceleration is equal to the what of the velocity graph at all times. Okay, I hope you thought to yourself slope. Acceleration is the slope of the velocity graph. Well, what is the slope of this velocity graph at all times? Just by inspection, the slope is 0. A horizontal line has a slope of 0. So that means that our acceleration here should be a line with a slope of 0 at all times. That's the acceleration graph right there. Now fill in the blank again. Velocity is equal to the blank of the position graph at all times. And again, slope. So now if we think about that, velocity is the slope of the position graph. Velocity has a constant negative value at all times. So therefore, we need to have a position graph whose slope has a constant negative value at all times. If we start from the origin, which is the information that we're given right there, then we want to create a graph that has a constant negative slope at all times. There's a lot of correct ways to do this. All of these straight lines that I'm drawing right now all have constant negative slopes at all times. So they're all correct. I'm just going to keep things clean and just draw one of them. Okay. So what again is the slope of this graph? Oops, pardon me. The slope of this graph is v0 at all times, which is a constant negative value. Good. Again, without any numerical values on the vertical axes, there's a family of correct solutions for what the position graph could kind of qualitatively look like. But they all have the same thing in common, which is they all start at the origin, and they're all lines of constant negative slope. All right, and then finally, let's try one that's a little more complicated. That's letter D. So for letter D, we're told that you have a little car that has a constant positive acceleration, shown here in this graph on the right, and it starts off with an initial negative velocity. Okay, so this is a little car that is initially going in reverse at a pretty fast speed, and then it has a constant positive acceleration at all later times. Well, what is the acceleration? What is that going to do to the velocity then as time goes on? Well, when you have a positive acceleration, that means that for every second that goes by, the velocity needs to become more positive. Well, if you're starting with a negative velocity, that would mean that as time goes on, the velocity should gradually become more positive, get closer to zero. Then, if we keep on accelerating, it'll just pass right by zero and become more positive after that. So notice it becomes more positive at all later times. That's what a positive acceleration does. So we would expect to have a velocity that does something like that. Notice that there's a whole family of correct answers, right? These are all correct. We don't even need to have it cross zero within the span of the graph because I didn't say it had to. Okay. But just to keep things simple, I'm going to just keep one. What's the slope of this graph? It's equal to the value of the acceleration, which is positive. And it's constant. Okay, now suppose that our little car starts at the origin, okay, as given in the problem. And now we want to create a plot whose velocity, whose slope starts out at a negative value and then becomes less negative over time, gradually touching zero, and then becoming more positive over time. So starts out with a big negative value, and then it gradually approaches zero, and then becomes more positive over time. So I'm thinking about the slopes here, right? So the slope starts out with a big negative value, and then it approaches zero, and then it becomes more positive over time. So if I sort of use a nice thick pen for that, then I'm looking at something like that. Now, again, there's a whole family of correct answers here that you could do for these parabolas. You could have a parabola that does something like that. You could have a parabola that does something like this. But whatever your velocity graph looks like, the time axes should match. So the two should harmonize. And what I mean by that specifically is notice that on our velocity graph, the velocity crossed zero at this time right here. So we can call that, well, I'll call that T1, okay? So that's when the slope of my position graph is zero. So in that case, this needs to be T1, where the slope is zero, or that needs to be T1, or that needs to be T1, where the slope is zero over here. So that needs to be the same, that needs to be at the same location on all of my time axes. Okay. So in that case, again, there's a family of correct answers for the velocity and for the position, but whatever you draw for one influences the other. So in this case, I would say that this one is the only correct one that matches the other graph. And the other two, we'll erase the other two. Okay, great. All right, that concludes this lecture. So please try the additional parts of problem 4 and 3 that we didn't do and check those against my solutions. And then try the credit problems in online homework number 5.